Hello all. In this video series, we are going to discuss trees, okay, which is one type of graph, and we will see the variations of isomorphism, that is one isomorphism and two isomorphism. So what is a tree? So tree is that type of graph which should be connected and which should be acyclic. Okay, so it is different types of graph wherein the two properties that you need to remember that it has to be connected as well as it has to be acyclic. Okay, so if a graph is connected, it means that the number of component that the graph will have is only one. Okay, so that means there will not be any disconnected component. Or it also means that starting from one vertex, you will be able to reach all other vertices. Okay, so there has to be path from each vertex to all other vertices. So since this graph is a connected graph, so it will have a path from each vertex to all other vertices. Now the second requirement of tree is it has to be acyclic, meaning that there should not be any cycle, okay, among any combination of vertices in the tree. So if there is a cycle, okay, among any of the vertices, then we will not be calling that graph as a tree. Okay, so for a graph to be called as tree, two property has to be satisfied. That is, it has to be connected as well as it has to be acyclic. Okay, so if a graph is connected, as I said, there will be a path, at least one path from one vertex to all other vertices. And since it is acyclic, since there is no cycle, which means that from one vertex, because there is no cycle in between, so from one vertex to all other vertices, there will be exactly one path. So it is only one path that will be possible from each vertex to all other vertices. So this is an example of a tree. So here you can see that this tree does not have any components, any other component except this one, and it is acyclic. So you can see in this graph there is nowhere you will be able to see any cycle being formed. Okay, so then we can say this type of graph as a tree. Now below figures are showing the different trees with different number of vertices. So the first tree is a tree with only one vertex. Second tree is a tree with two number of vertices. Third is with three number of vertices. Now in fourth and fifth, there are with four vertices, there are two types of trees that has been drawn. So it can be any form of graph can be called as tree, but the only requirement is that graph should be connected as well as that graph has to be acyclic. So now we will see some of the properties of tree which are very important. And the first property says that, as we discussed already, that between every pair of vertices there will be exactly one path. So why there will not be more than one path possible is because there is no cycle in between. Okay, so since there is no cycle, so there will be exactly one path that will be possible between every pair of vertices. The second property says that in a graph G, if there is one and only one path between every pair of vertices, then obviously that is a tree. So which is just the reverse of the first property. Now the third property, see here, if a tree is having n number of vertices, then how many edges it is going to have? Okay, so remember that we cannot have cycle, which means that the number of edges between any combination or among any combination of vertices cannot be more than one. Okay, so if you go back to the previous slide and try to see how many edges that is having with n number of vertices. So in the first example, when the number of vertices is 1, so number of edges is 0. In the second example, when the number of vertices is 2, the number of edges is 1. In the third example, when the number of vertices is 3, the number of edges is 2. So similarly, in fourth and fifth both, it is having 4 number of vertices, and in both drawing, it is, you can see here that the number of edges is 3. Okay, now you can draw this for any number of vertices and form a tree. You will be getting the number of edges exactly equal to n minus 1. Suppose if there are n number of vertices. So this is a very important property, that in a tree with n number of vertices there will be exactly n minus 1 edges. The next property says that in any connected graph with n vertices and n minus 1 edges, okay, so that is the property from number 3, then it will be a tree. So if you have a graph wherein n number of vertices is there with that n number of n minus 1 edges is there, and if that graph is connected, then that will be called as tree. Next property says that a graph is tree if and only if it is minimally connected. So minimally connected means it is connected with minimum number of edges. Okay, so that means in that one, for n number of vertices, you have exactly n minus 1 number of edges, which means that it means that in that n minus 1 number of edges, if you remove at least even if you remove one edge from that graph will become disconnected. So that is the definition of minimally connected. So that is nothing but in this tree, if you remove any of the edge, then this tree now will become disconnected. Okay, so this is a connected graph with minimum possible number of edges that is there. This is the next definition of tree, which says that if a graph has to be tree, then it has to be minimally connected. Okay, it has to be connected with minimum number of edges. Okay, if you reduce that number of edges even by 1, then the graph will become disconnected. So next says that a graph G with n vertices and n minus 1 edges without any cycle or the circuit, and if it is connected, then it will be a tree, or that will, if it is a tree, then it will be connected. So it's a vice versa. These following definitions are all equivalent. Okay, that is G is connected. Okay, and G does not have any circuit or the cycle, then that graph will be called as tree. Okay, as per the definition that we just saw. Otherwise, we can call graph G as a tree if it is connected and has n minus 1 edges. Or we can say a G is a tree if it does not have any cycle, or and it is having n minus 1 number of edges. Or a graph G can be called as tree if there is exactly one path between every pair of vertices. Or the fifth one is a graph G will be called as tree if that graph is minimally connected graph. So these are the 5 different definitions of a tree. Okay. Now in any tree, okay, where the number of vertices is equal to 2 or greater than 2, then the number of pendant vertices will be at least equal to 2. Okay, so there will be minimum 2 pendant vertices in any graph when the number of vertices is greater than or equal to 2. So next is a forest. So forest is nothing but a collection of trees. Okay, so it is a graph which is disconnected, but all its connected components are tree. Okay, so all its components are acyclic. Okay, so that is this example. So here in this graph G, there are 3 trees, and okay, all the 3 trees, they are nothing but the component of graph G. So we can say this graph G is a forest. So forest in simple word, it is a collection of trees. So next we are going to see how the various parameters of tree can be calculated. Okay, so herein we are going to see how the distance between the vertices is to be calculated, how to determine center of a tree, how to determine radius of the tree, how to determine the diameter and the perimeter of the tree. Okay, so the distance parameter will be in between the vertices. So that will be represented by small d in bracket the 2 vertices between which we want to determine the distance. So that is distance between vertex vi and vj is nothing but how many edges are there in between. Okay, so that is to start from vertex vi and to reach vertex vj, how many edges we need to traverse. That is called distance between vertex vi and vj. Now this distance has some property, so it is a function between two vertex x and y, and this is going to return a value or integer number that is nothing but the number of edges between those two vertices. So it has some property, and the first property is non-negativity property. That is, since it is a distance, okay, it is a number that is in between two vertices, this distance value can never be negative. Okay, there may not be any edge between two vertex. That is possible when both the vertices are same, or there has to be at least one edge between two different vertices. Second property says that the number of edges that is required to travel from one vertex to another is equivalent or equal to the number of edges that is required to travel in the reverse direction. Okay, so that is the distance between vertex x and y is equal to the distance between vertex y and x. Okay, whether you move in the forward direction or in the backward direction, it is going to give you the same value. The third property, that is triangle inequality, says that let's say that you have vertex x somewhere here and vertex y somewhere here. Now let us say the distance between vertex x and y is fx comma y. Okay, with this function you are getting the distance between vertex x and y. Now in between, suppose if you change this path, okay, so if you are changing the path, that is instead of going from x to y, let us say you are going from some another vertex, that is z. Then the distance between this vertex x and y will never be less than the distance from vertex x to z plus vertex z to y. Okay, if z is exactly in between x and y, then it will be exactly equal to. Otherwise, it is this particular distance, that is direct distance between x and y, will never be less than the distance while traveling via some other vertex, that is z. So which is nothing but when we are calculating distance, we have to find that path which is shortest. Okay, so shortest means you have to calculate the distance between two vertices by finding that path wherein there is least number of edges. So when we have calculated the distance by following the shortest path, then if we are again calculating the distance via some other node, then it is going to satisfy this triangle inequality property. That is, direct distance between x and y will never be greater than the distance from x to z and z to y. So next we are going to calculate center, radius, diameter and perimeter of a graph. And to calculate all this, we need to calculate a very important parameter, that is called eccentricity. Okay, so eccentricity is related to each vertex and it will be represented by E with that vertex name, that is V. So eccentricity of a vertex V in any graph G is the distance from V to the farthest vertex in that graph. That is, from that vertex, okay, determine which another vertex is in the farthest location, which means that from that vertex you need to calculate the distance with all other vertices and you need to find that distance, okay, which you will be getting from the farthest vertex. That means the maximum distance value. Okay, so eccentricity of a vertex is nothing but from the farthest vertex in that graph, how far is that vertex, okay, whose eccentricity you are calculating. So that is, from that vertex to the farthest vertex in the graph, you need to determine the distance, and that distance value in that graph will be the maximum value or the maximum distance of that vertex with all other vertices. Now that particular distance value will be called as eccentricity of that vertex. Now, in any graph, calculate the eccentricity of all the vertices and you find that vertex whose eccentricity is minimum or lowest. Okay, so that vertex with minimum eccentricity is called center of the graph. So that is, in this graph, let us calculate the eccentricity of all the vertices and that vertex having the minimum eccentricity. Okay, a vertex, okay, from whom the farthest vertex is giving you the minimum value, that will be called as center of the graph. So let us say for this vertex, its farthest vertex is this one and the distance that that it has with the farthest vertex is the number of edges, that is 1, 2, 3 and 4. So its eccentricity is 4. Similarly for this vertex, the distance with the farthest vertex is 1, 2, 3, 4. So its eccentricity is 4. Similarly for vertex C, its eccentricity is 2. That is whether it goes in right direction or in any of the direction. Okay, with any other vertices, it's the distance, maximum distance value that it will be getting. With all other vertices, it is 2. Similarly, for this vertex, it is 3, and for this vertex, it is 4. Okay, so what you need to do is, for each vertex, you need to calculate the distance with all other vertices, and the maximum or the highest distance value will be called as eccentricity of that vertex. So calculate eccentricity of all the vertices and the vertex with minimum eccentricity. So like in this case, it is vertex C, which is having minimum eccentricity, which is 2. Okay, this vertex will be called as center of this graph. So that is, this vertex lies somewhere in the middle. And radius is, as we know about the circle, okay, radius is the distance from the center to the circumference. So similarly, the distance from the center vertex to the farthest vertex is called radius, and this radius we have already calculated. That is nothing but the eccentricity of that particular central vertex. Okay, so remember this particular eccentricity, that is eccentricity of vertex C, is called radius of the graph. Okay, and this eccentricity we have already calculated, that is 2. So for this graph, its radius is equals to 2. Now one graph can also have more than one center, okay, that we will see later on the other examples, that in this example there was only one center, but it is also possible to have more than one center in a graph. But all the center, they are going to have same radius value, isn't it? So radius is nothing but the minimum distance. So if there was some other vertex giving minimum distance, then the other vertex would have been the center. So next, we are going to see diameter and the perimeter. So diameter, similar to that of circle, it is from entire distance, okay, from one end to the other end. Okay, so that is, to calculate the diameter, we need to find the maximum eccentricity of the, or nothing but the eccentricity of all the vertices, and that particular eccentricity value will be considered as diameter, which is maximum. Okay, so here we have already calculated eccentricity of all the vertices, and maximum eccentricity value is 4. Okay, which you are getting from 3 of the vertices. So this value 4 is considered as maximum distance from one end of this graph to the other end. Okay, so diameter of this graph is 4, and which all vertices are contributing for this diameter value 4. That those vertices are called perimeter of the graph. So let us further understand this using this example. So let's say this graph, okay, which is a tree, and it is having 10 number of vertices A, B, C, D, E, F, G, H, I, and J. So what we need to do is, here we need to determine the center, diameter, radius, and the perimeter vertices. Okay, so radius and the perimeter vertices. Now to determine this 4 parameter, as I said, we need to calculate the eccentricity of each vertex. So eccentricity of each vertex means the distance from that vertex to the farthest vertex. So for that, we need to calculate the distance from that vertex to all other vertices in this graph. So this can be drawn by making a table like this. So this table is n cross n table. So wherein n is the number of vertices in the graph. So write all the vertices in rows and all the vertices in column. So A, B, C, D, E, F, G, H, I, J, that is there in column as well as in the row. Now each entry of this table will be representing distance between the two corresponding vertices. Okay, so that is, first entry is the distance between vertex A to vertex A. Second entry is the distance between vertex A to vertex B. Now third is the distance between vertex A to vertex C. So this way you need to fill up this table. Okay, so every entry, as I said, is going to give you the distance between the corresponding vertex. Okay, now once you have calculated the distance, so how you are going to calculate the distance? By determining how many edges are there between those two vertex. So let's say between vertex A and vertex A, it is the same vertex, so the number of edges is 0. Between vertex A and vertex B, there are 2 edges, so the distance value is 2. From vertex A to C, there is only 1 edge, so distance is 1. So this is how you need to calculate the distance between all pair of vertices. Now once you have determined, eccentricity value, as I said, is nothing but the maximum distance value. So in each row you find that value which is maximum. Okay, so it is 0, 2, 1, 2, 3, 5, 5, 3, 4, 4. So maximum value is 5. So its eccentricity will be equal to 5. So distance from this vertex to the farthest vertex, which is F and G, the distance value is 5. So its eccentricity is 5. So similarly, in each row you calculate the maximum value. So in each row, the maximum value will be giving the eccentricity of the corresponding vertex. So once you have calculated the eccentricity of all the vertices, now from this eccentricity value, you can easily calculate these 4 parameters, that is center, radius, diameter and the perimeters. Now this is showing the rows from where we are getting the minimum eccentricity value. So minimum eccentricity value is 3, and which rows are contributing this minimum eccentricity value? There are 2 rows which from where we are getting this minimum eccentricity, that is row with vertex D and row with vertex H. So that means the radius of this tree, okay, so the radius of this tree is equals to 3, and which all vertices are contributing for this radius value, that is D and H. So these 2 vertices will be called as center of this tree. Now in this one we are determining the maximum eccentricity value. So from this column the maximum eccentricity value is 5. So there are 4 times we are getting this value 5, and this value we are getting from 4 different vertices, that is A, B, F and G. Okay, so we can say that these 4 vertices are the perimeter vertices, and these 4 vertices are giving us the diameter value. So for the graph that was shown previously, its diameter is 5 and its perimeter vertices are A, B, F and Z. So all of you should try this example. So there are 2 trees, T1 and T dash. You calculate the 4 parameter, that is radius, center, diameter and perimeter. Obviously you need to calculate the eccentricity of all the vertices. So you calculate these 4 parameters for these 2 trees. Now moving ahead, there are some special type of tree that belongs to rooted tree. So rooted tree is that tree wherein one vertex will be different in comparison to other vertices. Okay. Now that difference can be in terms of any characteristics. Like we can give that difference in terms of degree, or we can give that difference in terms of its properties, or it can be any other things. So what is a rooted tree? So a rooted tree is that tree wherein one of the vertex will have some special properties in comparison to other vertices. Now, like for example here, I can consider this vertex as a rooted tree. Maybe it has some characteristics which is not present in other vertices. So in this example, this particular vertex is a rooted vertex. So this type of tree wherein we are giving some special preference to one of the vertex, that will be called as rooted tree. We have another type of tree called binary tree, which is one special type of rooted tree. In this binary tree, there will be exactly one vertex with degree 2, and all other vertices will have degree either 1 or 3. Like for example in this one. So this vertex is having degree 2. Now if you see all other vertices, its degree is 1 or the degree is 3. Okay. Now you can just check for all the vertices, their degree is either 3 or 1. But there is exactly one vertex in this tree whose degree is 2. So this type of rooted tree is called a binary tree. Next is a very special type of tree, and it has lot of application in computer science in various problems in the computer science, that is spanning tree. Now spanning tree we will be determining from a graph. Okay, so in a graph, if I can find a walk or a path that traverse each vertex, okay, so if I can find a tree, okay, or a walk which should be acyclic, okay, that means there should not be any cycle or the circuit, and in that walk you are visiting all the vertices, okay, so a tree is nothing but the subgraph of a given graph. So a tree is called spanning tree of a given graph G if that tree is a subgraph of G and that tree contains all the vertices of tree. Okay, so that means for a given graph, you need to find a walk or a path wherein you should be traversing all the vertices of a given graph. Okay, and while traversing, you make sure that you are not forming any cycle. Then that tree, which is a subgraph from a given graph, will be called as spanning tree. Now, what is of interest to us, okay, in the computer science field and in most of the application area is a minimum spanning tree. So what is a minimum spanning tree is, suppose if given graph is a weighted graph. Weighted graph means the edges of that graph will have some number associated with it, okay. That number is called weight of the edge. Now, if the edges are having weight, the graph is called weighted graph. Now, in that weighted graph, if you want to find a tree, okay, which contains all the vertices, okay, the number of edges will obviously be less than or at least equal to the edges that is there in that graph. If you find a tree which covers all the vertices of that given graph, and if you add the weight of all the edges that belongs to that tree, if that is minimum, okay, in comparison to other possible trees that you may get from a spanning tree, then it is called minimum spanning tree. Okay, or in simple word, for any given graph you can have many possible spanning tree. Okay, like in this case we got this bold line as one spanning tree, but we can also traverse in some other form, like I can traverse in this way. Okay, if I traverse like this, then also I am covering all the vertices. So this way there are various traversal that is possible, which is not acyclic and which contains all the vertices of given graph. It is possible, so more than one spanning tree is possible, but among all the spanning tree, so from given graph you find all possible spanning tree, and that tree whose the total weight of all the edges, okay, that you will be getting by adding the weight of all the edges. So if the total weight of that particular spanning tree is minimum, then we say that particular spanning tree as a minimum spanning tree. So this graph, which is a weighted graph, you can see here, uh, to get a tree, okay, that should be covering all the vertices of this given graph, there are various possible tree, okay, various tree that you can get from this graph. But among all the tree that is possible, all this bold line, okay, the black line or the black edges, if you take, then it is forming the tree from this given graph, and this particular tree is a minimum spanning tree. Now, some of the things that we need to know with respect to spanning tree is the edges that you will be taking from a given graph, okay, and that you are considering or including it in your spanning tree, then that edge is called branch of that spanning tree. Now with that, all other edges of that given graph which you are not taking in your spanning tree, that all those edges are called chord. Now as I said that if your graph is a tree, then the number of edges in that graph will be exactly equal to the number of vertices minus 1. So which means that in a spanning tree also, if your given graph had n number of vertices, then your spanning tree will be having n minus 1 number of edges. Now with this one, you can calculate how many chord it is going to have. So let us say E is the total number of edges in a given graph, and out of this total number of edges you have taken n minus 1 number of edges to be part of spanning tree. So that means n minus 1 number of edges are branches of your spanning tree. Now if you perform this operation, that is E minus n minus 1, so that means if you exclude this n minus 1 number of edges from total edges of this graph, then remaining or the left out edges will be called as chord of the given graph. So how many chord will be there with respect to each spanning tree for a given graph is E minus n plus 1. And this number of branches is also called as rank, and the number of chord with respect to each spanning tree is also called as nullity. Now this k is the number of component. We can also have a graph with more than one component, and you may try to find the spanning tree of each component. So if your graph is having k number of component, then its branches, okay, branch or nothing but the edges that you have taken for the spanning tree will be n minus 1, n minus k, and nullity or the chord will be equal to E minus n plus k. So all in all, rank is nothing but the branches of a spanning tree. So all the edges from the given graph which you have taken to be considered as part of a spanning tree are called rank. Nullity is all the edges which you are not taking in your spanning tree. Okay, so that means your total edges is divided into two. One is the branches, the other rest of the edges will be the chord. So number of branches is called rank, and the number of chord is called nullity. And obviously the number of rank, if you add with the number of chord, that is nullity, it is going to give you the total number of edges in a given graph. Consider these two questions, that how many spanning tree is possible in a complete graph with n number of vertices. That is nothing but, let us say you have a complete graph with 4 vertices. Complete graph means a graph wherein all the vertices will have edges with all other vertices. So let us say this is my complete graph with 4 vertices. So how many spanning tree is possible in this graph? So with these 4 vertices, you have the edges, and you try to take the minimum number of edges that should contain all the vertices. So you can take this edge, okay, a minimum and there are various possible combination. So you can try taking the various possible combination, that is minimum number of edges which should contain all the vertices of this given graph. So how many the spanning tree is possible? Or another question is, how many label tree can there be in a graph with n number of vertices? So both the questions are same, and the answer to both the question is, let us say if the number of vertices is 2, okay, then the maximum number of edges that this graph can have is only 1. So with this one, how many tree is possible? So there is only one tree that is possible. Now if the number of vertices is 3, then the maximum number of edges that this graph can have will be 3. And how many spanning tree is possible? So one spanning tree is, if you take that is this one, this is one spanning tree which is possible. Another spanning tree that is possible will be this one. Okay, third spanning tree that is possible is this one. So you have, with 3 vertices, you have 3 spanning tree which is possible. Now similarly, if the condition is this one, that is with 4 vertices, how many spanning tree is possible? So the solution is given by a very famous formula called Cayley's formula. and it says that for n number of vertices in a graph, the number of spanning tree that will be possible is n raised to power n minus 2. So if we apply this formula for n equal to 4, that is in this graph, okay, with n equal to 4, how many spanning tree will be possible? So that is going to be equals to 4 raised to power 4 minus 2, which is 4 raised to power 2, which is equal to 16. So if you have a graph with 4 vertices, then maximum number of spanning tree that will be possible is 16. Now what is the minimum spanning tree is? Now in maximum of 16 possible spanning tree, you need to find that spanning tree with minimum weight. So for that you need to calculate the weight of all the edges, add the weight of all the edges, the result will be the total weight of that spanning tree. And the spanning tree with minimum weight, total weight, is called minimum spanning tree. Next theorem is Kirchhoff matrix tree theorem, which says that if the number of n increases to very large, okay, here in this example the number of n was only 4. With 4 also you are getting 16 possible spanning tree, okay. Now when this value of n becomes very large, let's say 100, 200 and all, now in that to find all possible spanning tree will be very difficult, okay. It is going to take a very large amount of time, that is exponential time. But as per Kirchhoff matrix tree theorem, we can use the function of determinant. So determinant of LG of I, with this one you can calculate the number of spanning tree for any graph with n number of vertices in polynomial time. Okay. Next is fundamental circuits. We know that spanning tree is a tree. Okay, so that means it will not have any cycle. Now, why it will not have any cycle is because from the given graph, we took minimum number of edges. Okay, that will include all the vertices and that will not form any cycle. So, if we have taken minimum number of edges, that means there is no cycle. Now, the rest of the edges in that graph, as I said, is called chord. Now, the property of a spanning tree is, in that spanning tree, if you take any one chord from the given graph and add to your spanning tree, then it will form a cycle. Okay, so let us see this in this example. This is a graph with 5 vertices and it is having 8 number of edges. So out of 8 edges, if you take 1, 2, 3, 4. So if you take 4 edges, then it is including all the vertices of given graph. So this becomes a spanning tree. So here T1 is one of the spanning tree. Similarly, another possible spanning tree is T2. So here we are taking separate set of edges and we could include all the vertices of given graph. Now in T3 also, with 4 edges taking from this given graph, here also we could include all the vertices of given graph, so it is also a spanning tree. Now in any of the spanning tree, it is having minimum number of edges. So since the number of vertices in this graph was 5, every spanning tree is going to have exactly 4 number of edges. Okay. Now in this 4 number of edges, if you take at least one extra edge, okay, that is the chord from the given graph with respect to that spanning tree, then you will be getting a cycle. That is nothing but, let us say in this example, in the first spanning tree, that is T1, you have taken edges A, B, C and D. Okay. Now other than this, if you take any other edge, like if you take edge E and add it here, then you are getting one cycle. Okay, so similarly if you take another edge, okay, that will be called as chord with respect to this spanning tree. So let us say this edge G, okay, if you bring this edge G from given graph and add it here, you will be getting one cycle. Okay, so previous cycle that you got was here by adding the edge E. So similarly if you bring this edge H and add it here, then you will be getting the third cycle. Okay, similarly there is one more edge, that is F. If you bring from here and add it here, then you will be getting one more cycle. Okay, so on addition of each chord you are getting one cycle. or one circuit in your given graph. So that circuit which you have formed by adding the chord from the given graph is called fundamental circuits. So how many fundamental circuit is possible in each spanning tree or with respect to each spanning tree? Yeah, by one chord you are getting one fundamental circuit. So how many fundamental circuit is possible? That will be equal to how many chords are there. So how many chord you can calculate, that is by using the formula, that is E minus n plus k. So if the graph has more than one component, then the number of component is called k. Okay, so the number of fundamental circuit in each with respect to each spanning tree will be equal to the number of chord. Similarly, if you take the spanning tree T2, then taking each chord, it is going to give you one cycle. So this is one cycle. Taking another chord, you will be getting the next cycle. Taking third chord, you will be getting the next cycle, and taking the fourth chord, you will be getting the next cycle. So the number of fundamental circuit that you are getting here is also 4. Because we have 4 chord, so in all possible spanning tree, you are going to get 4 chords or the 4 fundamental circuits. So next we are going to see cut sets and cut vertices of a graph. So cut set is the number of edges, how many set of edges, removal of which will make your graph disconnected. Okay, but that set of edges has to be minimal, which means that its subset should not be disconnecting your graph. So let us see that with this example. Let's say this is a graph G. In this graph, if I remove some edges like A, C, D, and F. Okay, if I remove these 4 edges from this graph, then what will happen is once these 4 edges will be removed, it is going to partition this graph into 2 parts. In one part you are going to have this portion. So this will be in one part. In another part it is going to have this many vertices with these edges. So that means the resultant graph is going to look like this. So how we got this graph is by removing 4 edges, that is A, C, D and F. Okay, so we have a set that is A, C, D and F, and removing these 4 edges, okay, that is there in this set is making your graph disconnected. Then if this is true, then we say that the set is a cut set. Okay, but one important thing is that set should not have its subset again the cut set, which means that I cannot consider, let us say if I'm taking a set A, C, H and D. Okay, so taking these 4 edges A, C, H and D. So A is here, C is here, H is this edge and D is this edge. Okay, if you remove these 4 edges, okay, with this one, then also the graph will be disconnected. That means in one side you will be getting this component and in another side you will be getting this component. So graph becomes disconnected, but we cannot call this set a cut set. Okay, why we cannot call this set as a cut set is because its subset, that is subset with only 3 edges, that is A, C and H, is going to disconnect the entire graph. So when you have, for a given set, when you have another set which is the subset of that given set is also disconnecting that given graph, then we cannot call that set as a cut set. So as per the definition, it says that for a set of edges to be cut set, its proper subset should not be another cut set. So that means its proper subset should not be disconnecting the entire graph, which means that in that set, it has to have minimum number of edges that should be disconnecting the entire graph. So another example is, let us say I can have a set with edge k. Okay, so this is again one example of a cut set, because if I remove this particular edge, that is k, from my given graph, the graph will have this portion in one side and one vertex, that is v3, in the other side. So again the graph will become disconnected. Similarly, other examples are I can have a cut set with edges as A, B and G. I can have another cut set with these edges. Okay, I can have another cut set, this one. I can have another cut set. Okay, next cut set can be this one. So this way there are various cut sets which is possible. So cut set is the set of edges removing which will make your graph disconnected. And this cut set is also called as cocycle. So why it is cocycle is because, so let me draw one cut set. So let us take one cut set as an example. So I have a cut set that is A, C, D and F. Okay, by only using these four edges, let me draw the graph. Okay, so with this cut set A, C, D and F, we are getting this graph. Okay, so this is a subgraph from a given graph, which is a cut set. That means removal of these four edges will make your graph disconnected. Now, the cut set is also called cocycle is because if you add at least one edge in this graph that you have formed by using the cut set edges, then you will be getting the cycle. That is, in this graph, if you add one extra edge, okay, that edge you can add anywhere. Adding one extra edge, you are getting a cycle. Okay, so cocycle means it is just about to be a cycle. So adding one edge, it will become a cycle. So that is called cocycle. So these are some of the properties of cut set, that every cut set must contain at least one branch of a spanning tree. Why it has to be true is because if a cut set does not contain any branch of the spanning tree, then that is not going to disconnect a graph, because for a given graph, okay, every possible spanning tree is a tree that is a connected subgraph of that given graph. So at least one branch of every spanning tree has to be present in every cut set. Now the same thing has been defined in the other way, that is, in any connected graph, the minimum number of edges, okay, and that has exactly or at least one branch of every spanning tree, then it will be a cut set. Okay, so if it does not contain any of the branches, okay, from any of the spanning tree, then that is not going to disconnect a graph. Now every circuit has to have even number of edges in common with any cut set. And the last one says that if we perform ring sum operation with any two cut set, then either we will be getting the third cut set or we will be getting edge disjoint union of cut set. That means our resultant set will not have any edges in common. So let us see in this example. So let us take these two cut set, that is A, C, D and F. That is A, C, D and F is this one. And another cut set as, let us say, A, B and G. That is this one. So if you perform ring sum of these two, then what it is going to give you? The ring sum is going to give you all the vertices, but the edges, which is either in two of the sets, okay, the common edges will not be taken. So with this one, my resultant cut set will be, it will have the edges, that is C, D, F, B and G. So in this two set, we have common edge as A, so A will not be taken in the resultant cut set, and all other edges if you take and form the set, then it is going to have this many edges, that is G, B, C, D and F. Okay, now this many edges also if you remove from your given graph, then this is dividing the given graph into two halves. So it is making your graph disconnected. So it is again another cut set. Okay. So that is nothing but between two cut set, if there is any edge that is common, then the resultant cut set, okay, after performing the ring sum operation, the resultant set will also be a cut set. Otherwise, those two sets, if they do not have any edge in common, then the resultant set will have a edge disjoint set. So that means all the edges are unique. This fundamental cut set is related to spanning tree. Okay, suppose for a given graph we have got a spanning tree. Let us say this bold line is the spanning tree of the given graph. Now, if you are finding a cut set, okay, all possible cut set which includes exactly one branch of spanning tree, like for example this cut set, it is having exactly one branch of the spanning tree, like this one, which is having one vertex in one side and all other vertices in the other side. So this is also a fundamental cut set. Now if I take this cut set, okay, that is removing these four edges will also make this graph disconnected, but it is not a fundamental cut set because it is having more than one branches of that spanning tree. So fundamental cut set is with respect to a spanning tree that every cut set that includes exactly one branch of a given graph, that is called fundamental cut sets. So these are the possible fundamental cut set in the graph. So in your exam, you may not be getting to find all possible cut set, but you may get a question to determine all possible fundamental cut set with respect to a given spanning tree. Okay. So next we are going to see connectivity and separability of a given graph. So connectivity is related to connectedness, okay? How to define whether a graph is connected graph or not, okay? So when can we say that the given graph is connected is when there is a path between every pair of vertices. So that means starting from a vertex, you can reach to all other vertices. That is a connected graph, and the path that is used is called connectivity of the graph. Now, if the graph is such that between some two vertices, if it is not possible to move or traverse, then the graph will be called as disconnected graph. Bond is nothing but the cut set that is going to find that set of edges which will be dividing the entire graph into two components. Now, there are two terms which is very important, that is edge connectivity and vertex connectivity. Okay, so edge connectivity means minimum number of edges. Okay, for any given graph, if you remove that many edges, then the graph will become disconnected. Okay, so in some graph, removing one edge can also make it disconnected. In some graph, you might have to remove two edges, three edges, four edges, or so on. Okay, it depends on the type of graph. So minimum of how many edges you must remove from your graph to make your graph disconnected, that is called edge connectivity. Okay, or else edge connectivity is nothing but the size of smallest cut set. So as we have discussed previously that one graph can have many possible cut set, and each cut set is going to give us the set of edges, removal of which will make your graph disconnected. Now out of all the cut set having minimum number of edges will give us the edge connectivity, and this edge connectivity is nothing but a number, that is the number of edges, removal of which will make your graph disconnected. So similarly, vertex connectivity is also the minimum number of vertices which if you remove from your graph will make your graph disconnected. Okay, disconnected here means there has to be at least two connected component. Okay, disconnected does not mean that removing the end vertex and the resultant graph cannot be a disconnected graph. So this we will see here. So let us take in this graph. So in this graph, if you try to see, then minimum of how many edges you need to remove to make this graph disconnected. Okay, so let us see here. If you remove these three edges, okay, then these three edges will make removal of these three edges will make your graph disconnected. That is, you'll be getting two component, but it is not the edge connectivity of this graph, because there are other set of edges like this one, that is h and k. If you remove these two edges, then also the graph is becoming disconnected. That is, in one side you have only one vertex, and that will give you the null graph, and in other side you have the remaining number of vertices. Now this was two number of edges. Now can you find any edge, okay, removal of which will make graph disconnected, or single edge removal of which is going to make this graph disconnected? No, right? So here also removing two edges can make your graph disconnected. So what is the edge connectivity of this graph is? The edge connectivity of this graph is 2, because minimum of two edges you must remove from this graph to make this graph disconnected. Now we will say vertex connectivity. So vertex connectivity, as I said, removal of minimum number of vertices that will make your graph disconnected. Okay. So let us see this thing. Suppose if you remove this vertex V1, okay, then what will happen? Its incident edges will also be removed. While removing a vertex, its incident edges will also be removed, and you will be left with this portion of the graph, okay, which is not a disconnected graph, remember. Okay, it is only the subgraph of given graph, but it is still connected. Okay, it does not have more than one component. It is still having only one component. Okay, so that means removing one vertex from this graph will not make this graph disconnected. So how many vertex you must have to remove? So that is, let us say if you remove this vertex V2 and V3, okay, removing these two vertex will remove all the incident edges, and you will be getting a disconnected graph. That is, in one side you have only one vertex, that is V1, and in other side you have all other vertices, that is V4, V5 and V6. Okay, so that means minimum of how many vertices you need to remove from this graph is you need to remove at least two vertex, then only the graph will become disconnected. So its vertex connectivity is also 2. Now in this graph, we try to find the vertex connectivity and edge connectivity. So edge connectivity means minimum number of edges. So let us say if you remove these two edges, okay, then the graph will be disconnected. But removal of single edge is not going to make this graph disconnected. So for this graph, its edge connectivity is 2. Now what is the vertex connectivity of this graph? You can see here the this 4 outer vertices if you remove, then resultant graph will be still connected, so that cannot be called for the vertex connectivity. But this middle vertex if you remove, okay, this particular vertex if you remove, then this graph will be disconnected. So for this graph, its vertex connectivity is equals to 1. Menger's theorem says that the edge connectivity also gives us the information about maximum of how many paths can be possible between two vertices. Okay, that is, here let us say the edge connectivity is 2, which means that between any two vertices the maximum number of paths, okay, possible path can be 2. So till now we have been discussing about connectivity. So now we are going to see separability. Okay. So when can we say that a graph is separable is when we have cut vertex in that graph. So cut vertex is nothing but for that vertex, its vertex connectivity is 1, and which vertex is contributing for this vertex connectivity 1. That particular vertex is called cut vertex. Okay. So if a graph has a cut vertex, so that means if your graph has one vertex which is such that which is present in every path between all other vertices, that is nothing but if you remove that cut vertex from your graph, then your graph will be disconnected. Okay, which further means that there will not be path between some pair of vertices at least. So if your graph has a cut vertex, then that graph is called a separable graph. And obviously a cut vertex is one vertex, removal of which is making your graph disconnected, which means that the vertex connectivity of your graph will be equal to 1. So for example, here in this graph we have a vertex V, okay, and this vertex is a cut vertex because if we remove this vertex, then entire graph will be disconnected. And this is a separable graph because it has a cut vertex or its vertex connectivity is equals to 1. There are some uh, uh, properties related to separable graph, and that is a vertex V in a connected graph G will be called as cut vertex. So if there exist at least two other vertices x and y such that that vertex V is present in every path between x and y. Okay, like for example, here vertex V is a cut vertex because this vertex V is present in every path between there are at least two other, let us say vertices, let us say this is x and this is y. Okay, so between this vertex x and y, in every possible path, this vertex v is there. So that is why removing this vertex v, we could not have any path between these two vertex, that is x and y. So the first property says that for a vertex to be cut vertex, it has to be present in every path, okay, between at least one pair of vertices in that given graph. The next property says that for any given graph, its edge connectivity will always be greater than or at least equal to the minimum degree of that vertex. Okay, so minimum degree of any vertex in that graph. Okay, suppose if you consider a graph and consider a vertex with minimum degree. Okay, now that degree is defining the number of edges that is incident on it, and with this one, if you remove that many edges, it is also going to make your graph disconnected. So that is, its edge connectivity will always be greater than or equal to minimum degree of any vertex in that given graph. Similarly, the third property says that the vertex connectivity of a graph will always be greater than or equal to edge connectivity. This is because the vertex connectivity defines the set of edges which will also be removed if you remove a vertex. So then it should always be greater than or equals to the number of edges, minimum number of edges, removal of which will make your graph disconnected. So next we are going to see two types of isomorphism, and this is related to separable graph, that is one isomorphism and two isomorphism. Okay, so we know that a separable graph is that graph which will have a cut vertex. Okay, and what is a cut vertex? It is that vertex removal of which will make your graph disconnected. Okay, now from that cut vertex, both the side of the graph will be called as blocks. Okay, let us go back to the previous example. Now in this one, V is our cut vertex. So now if you make two copy of this vertex V, and if you separate this graph, okay, one copy of V in one side, another copy of this vertex V in other side, then you will be getting two component. Okay, these two component of a separable graph is called blocks. Now suppose if you are given with two graph G1 and G2, you can call these two graph one isomorphic. Okay, if they become isomorphic after applying this operation 1. So what is this one isomorphic is? In the last video we had discussed about the isomorphic graph. So two graph are isomorphic means they are equivalent. Okay, they are actually the same, but it is just their representation is different. But what is one isomorphic? So one isomorphic graph are not directly equivalent graph. Okay, so their mathematical representation will also not be same. But if you perform this operation 1, which we are going to discuss next, in one of the graph, okay, if you perform the operation 1 in such a way that after performing operation 1, the resultant graph becomes isomorphic to the other graph, okay, which you have got, then we can say that the two graph are isomorphic to each other. Okay, so let us see this operation. So as per this operation, what we can do is we can split the cut vertex into two. That is, that cut vertex we can make the duplicate copy of this, and based on that we can divide the graph into two part. Okay, and after splitting, you can join the different components, okay, in such a way that may look similar to that of other graph. So that means that becomes isomorphic to the other graph. So after repeatedly applying this operation 1, if you can form the resultant graph, okay, as isomorphic to that of original graph, then we can say that the two graph, that is G1 and G2, they are isomorphic to each other. That is, for example, let us say this is my graph G. So in this graph there are various cut vertex. So this is one cut vertex, this is another cut vertex, and this is the third cut vertex. Now in each of these cut vertex, okay, let us make the duplicate copy of this and let us divide the graph. Okay, so with this one, for this first cut vertex, let us make 3 duplicate copy and divide the entire graph into 3 part. Okay, so this is the first part, second part, and the third part. Similarly, for the second cut vertex, divide it into two parts. Now similarly for the third cut vertex, again divide it into two parts. So how many blocks that you got? 1, 2, 3, 4 and 5. Okay. Now suppose if you are given with on some another graph that is G2, and G2 is something like this. So let's say our graph G2 looks like this. Okay, though the diagram is not very clear, but just try to understand this. And here, okay, I need to prove that this G1 is one isomorphic to G2. Okay, if you try to prove isomorphic between these two graphs, then it is not possible. Okay, because you will not get the corresponding one-to-one correspondence between vertices and the edges. That you will not get. But let us see whether this two graph is one isomorphic or not. So for that, what we are doing is we are dividing the entire graph into separate blocks like this, and let us try to join this separate block. Okay, in some you just try to use the different combinations and try to get this graph whether it is possible or not. Okay, now let us say this first block, okay, and use it here. Now let us take this block and combine with the previous block. Okay, now let us take this block, okay, and join it here. Now let us take this block and join it here, and let us take this first block and join in the last place like this. Okay, so once you join all this thing, then you are getting this graph G2. Okay, so if it is possible to get graph G2 after applying that operation 1 and combining the various blocks, okay, based on how G2 looks like, then we can say that graph G1 and G2, they are isomorphic to each other. Now the next one is two isomorphism. So two isomorphism says that two graph can be called as two isomorphic graph if they become isomorphic after repeatedly applying operation 1 and operation 2. That is, as per operation 1, if there is a cut vertex, then you can divide the graph, okay, from that cut vertex by creating the duplicate copy of that cut vertex, okay, and different blocks can be combined, okay, based on the result that you want to get. Now operation 2 talks about the vertices which is not cut vertex. Okay, so even if your graph is not a separable graph, that is, it is not having any cut vertex, then also you can divide the vertices. Okay, or you can create the duplicate copy of the vertices and you can divide the graph from that vertex. So let us see, if I have a vertex x, you can divide the vertex x into x1 and x2. Similarly, you have another vertex y and you can divide this vertex into y1 and y2. Now you can again combine those two separate graph. Okay, so let us say you are combining x1 with y2 and x2 with y1. Okay, or in some other combination, okay, whichever you feel that is going to give you the result. And after rejoining, if the resultant graph is isomorphic to the original graph, okay, or to the other graph that is provided, then you can say that the two graphs are isomorphic to each other. So that is nothing but, let us say I have this graph G. Okay, I need to prove this graph isomorphic to some other graph. Okay, so for that, what we are doing is we are taking two vertex x and y, and we are making two copy of these two vertex. That is, x we are making x1 and x2, and for y we are making it as y1 and y2. Now previously x1 and x2 were connected and y1 and y2 were connected. Now you want to reverse it. Okay, so you are simply inverting this particular block. So I'm inverting this block. Now here y1 we are connecting with x2, so y1 and x2 we are making it as one vertex. Similarly, x1 and y2 we are making it as one vertex. So after joining these two, you are getting this resultant graph. Now this resultant graph, if it is isomorphic to the other graph that is provided to you, then you can say these two graphs are two isomorphic. So that is, let us say this is G1 and this is G2. You can say that G1 and G2 are two isomorphic to each other. So this was for today's lecture, and in the next lecture we are continuing with the planar graph, okay, and how to detect the planarity of a given graph. So till then, bye bye.